In this video, we're going to be deriving the basic kinematics equations, which are shown right here, using algebra. In another video, I do it using calculus. So what we're going to start with is just some basic ideas. We're going to start with our definition of acceleration as simply being the rate at which velocity changes, delta v divided by delta t. And we're going to use this equation right here, which we haven't really derived. We're going to argue that it certainly makes sense that the average velocity is just the arithmetic average of the initial velocity and the final velocity. And that is simply defined to be the displacement divided by the time interval. And here we're just going to argue this makes sense because if we take and graph velocity versus time, and we have constant acceleration, which is where all of these come from, that is just a straight line. And this right here is the initial velocity. This right here would be the final velocity. And this right here would be the final time. And it kind of makes sense that at the midpoint of the time interval, the average velocity would in fact be, the line back where it belongs, the midpoint between the initial and the final velocity. At this right here would be the average velocity. In the calculus video, we actually derived this rigorously. So this is true. We're just arguing here that it makes sense that it's true. Using calculus, we can derive it. And here we're just going to accept it. So here we're going to start with these two equations right here, the definition of acceleration and the idea of average velocity. And we're going to derive the equations right here. So what we're going to start with is taking our average velocity, let's go into red, let's use black. Average velocity is the final velocity plus the initial velocity divided by 2, which is delta x divided by delta t. Now delta x is the final position minus the initial position. Delta t will always be a change in time, which is the final time minus the initial time, and we'll always use the convention that we'll start at t equal to 0. Now what I'm going to do is take this equation and simply say this means x minus x0 equals essentially this term right here times t. So this is equal to v final plus v initial divided by 2, all of this times t. Now we also have our other equation, which tells us the acceleration is the change in velocity divided by the change in time, and that is equal to the final velocity minus the initial velocity divided by delta t, which again is t minus 0, but we'll drop the 0. Now we're going to take this equation and solve it for the final velocity. The final velocity will be the acceleration times time plus v0, just taking this equation and rearranging it. Now what we're going to do is combine these two equations and take this right here, and we're going to substitute it in for the final velocity right there, and then just rearrange terms and simplify. So this is equal to final velocity. First I'm going to take the 1/2 out and write it as a 1/2 rather than dividing by 2. Final velocity is just acceleration times time plus v0 plus another v0, that's 2v0. So that's what's inside the parentheses. I have to remember I still have a time t right here. So that's the 1/2. So all the terms have been accounted for. Now what we're going to do is take this and just multiply it out. So this is equal to 1/2 a times t, this t, times that t, which is t squared, plus 1/2 times 2, which is 1, times v0 times t. Now all we need to do is simply take the x0, bring it to the other side, and rearrange these terms, and we have our first equation. X is x0 plus v0t plus 1/2 at squared. So this right here is equation number 1. Equation number 2 is in fact this term right here, which just came from our definition for acceleration. We just rearranged the terms and solved for the final velocity. So we have our first two equations. Now we need to derive the interesting equation, which is the third one. To derive the third one, I'm going to first write down the first one as the x final minus x initial, and that is just what I mean by delta x. And that is equal to the initial velocity times time plus 1/2 at squared. That is just the first equation, rewritten a little bit, bringing the x0 over to the other side, and noticing the final minus the initial position is just what we mean by delta x. Then we're going to have our second equation, which said that the final velocity is equal to the initial velocity plus acceleration times time. Now the third equation just comes from eliminating t. So we're going to solve this for t, and then take and substitute that into t over there, and then simplify the resulting mess. So we solve this equation for t, and t will simply be the change in velocity, final minus initial, divided by the acceleration a. Plug that into here, and we get delta x is equal to v0 times t, which is this expression, v final minus v initial divided by a, plus 1/2 a times this expression squared, v final minus v0 divided by a squared. And as you can see, it's a mess. So all we need to do is simplify this and rearrange terms, because this is actually the third equation. It's just a messy form of it. Now, here I'm dividing by a right here, and here I'm dividing by 2. I don't want to be dividing by anything, so I'm going to take the whole equation right here, both sides of it, and multiply it by 2a. That doesn't change anything so long as I treat both sides the same. So then what we're going to do is just simplify that. So I have 2a times delta x. You know, we can see it's beginning to take form because that's one of these terms we want, is equal to 2a, and here I'm dividing by a, so all I have left is a 2 times v0 times v final minus v initial. And over here on this part, the 2 is going to cancel out, and I have 2a, so that's a squared, times, again, just write down this expression, v final minus v initial divided by a, and the whole mess squared. Now we can do some more simplification, because here I'm multiplying by a squared right here, and I'm dividing by a, which is squared right here. So this and this are going to cancel out. Then we need to take and just multiply all this out and simplify. So this is 2 times v0 times v final minus 2 times v0 squared plus, and all I have to do is basically multiply out this square right here, and that will be plus v final squared minus the cross term v final times v0 plus v0 squared. And it looks messy, but it simplifies, because here I have a plus 2v0 v final, and here I have minus the same expression, so those cancel out. And over here I have plus 2v0 squared, and over here I have minus 2v0 squared, so that partially cancels out. So we end up with, I still have my v final squared, and then minus v0 squared, and I'm almost there. Now we're going to go to a new screen and just write what we have so far. We have 2a delta x from one side of the equation. The other side had the final velocity squared minus the initial velocity squared. Now all we need to do is rearrange terms, and this right here says the final velocity squared equals bringing this to the other side of the equation, v0 squared plus 2a delta x, and this right here is in fact equation 3. So we have now gotten the first 3 equations. Then we can go back to the first slide, right here, and notice we have this right here is the 4th equation, and we kind of assumed this to be true and just argued that that was true. So now we have all 4 equations derived from algebra, with the 4th one being kind of hand-waving, and this one, to formally derive, does require a little bit of calculus, which was done elsewhere. So we are done.
What we're going to do here is a slightly better description as to how we got equation 4. It does in fact require a little bit of calculus, but the only thing we really need is that when you draw a velocity time graph, the area under the curve is in fact the displacement or the change in position. If we have a constant acceleration, the velocity graph, of course, is a nice straight line. That means the area under the curve will in general be a trapezoid. So the displacement, delta x, is the area of a trapezoid. And if you remember a little bit of geometry, the area of a trapezoid is 1/2 the sum of the 2 bases multiplied by the height. We take this formula and we apply it to our trapezoid on our velocity time graph. We'll find that the 2 bases are the initial velocity and the final velocity. So 1/2 the sum of the 2 bases is 1/2 the initial velocity plus the final velocity, and the height is delta t. So the area, which is displacement, is 1/2 of the sum of the 2 velocities times delta t. We're going to take this equation, divide both sides by delta t, so we get delta x divided by delta t, and that is just the average velocity, equals 1/2 the sum of the initial and final velocities, which is equation 4.